Okay, thank you for introducing. Hi, I'm Wonkyung from Seoul National University, and today I'd like to talk about restructuring batch normalization to acceleration and training. So let's begin. So why do we care about accelerating training? Because training requires high computing costs, which may take several days to weeks to train a single model. For example, in ResNet, we need 29 hours with 8 GPUs, which is quite large cost. And also, this training might be done multiple times to follow up new algorithms or new models or data set. So in this work, our focus is on reducing computing cost of the training. Then why do you care about the batch normalization? Should we concern beyond even if convolution or fully connected operations are dominating training time sometimes? So this is a chart showing execution time breakdown by layers on training different CNN models on a single machine. We see that the conv/FC, convolution or fully connected layers are dominant on those shallow networks such as AlexNet or VGGNet. However, in those deep and recent networks such as ResNet or DenseNet, they become less dominant. This is because those models heavily use BN as well as conv, and also they use smaller conv filters, reducing convolution computation task, and there are also new layers supporting skip connections, such as concatenation or the element-wise operations. So for those networks, non-conv layers, which are other than conv/FC, are becoming heavier, and the BN, especially the blue bar, takes up a large portion among those non-convs. So interesting point here is that these non-convs are typically bounded by the memory bandwidth. So to see the memory bandwidth bottleneck of these non-convs and potential speedups without the bottleneck, we did a simple experiment modifying some codes of a framework, and we turned every main memory access of BN and ReLU into L1 cache hits, so that thereby giving infinite memory bandwidth effectively. So in that hypothetical machine with infinite bandwidth, we get large speed of about totally 60% on DenseNet. And definitely this is not possible in real hardware. We cannot provide the infinite bandwidth. So what we do instead to remove, to reduce the memory access on those non-conv layers are layer fusion technique. So what is layer fusion? Each recent model, CNN model, usually has its own repeating basic layer patterns, whatever it is called composite layer in DenseNet or the residual block in the ResNet. So here, what layer fusion does is that basically fusing the adjacent layers into a single fused layer. For example, here we can fuse the batch norm and ReLU together, making a single fused layer. So here comes the question, can we fuse all these layers together in a basic block in a training recent CNN models, so will they work well? To answer that, let's look at the basic data access patterns of a popular layer. Say, we have input feature maps having dimensions of she channels along with height and width, and also there are n independent images, which is definitely the batch size. So let's say we have a convolution layer here. So for each weight filter in this convolution, these filters slice through the input feature maps, thereby making alpha feature maps of alpha channel. And here comes another weight filter, which also slices through the input feature maps and thereby making alpha feature maps on the different channels. So here, if we consider the total size of input and output feature maps of a whole batch, it does not fit into an on-chip memory typically. For example, on the right side, we have some conv layers from the DenseNet, and in each conv, the total feature maps are typically over megabytes or sometimes up to several hundreds of megabytes, requiring large off-chip memory access on these conv layers. So if we use larger batch size, for example, more than 100, which is a common case, the size could be way larger. So how to deal with that? So let's say we have another element-wise layer after convolution. For example, we can have a ReLU layer after convolution. So in this case, we can fuse them. We can fuse the convolution and ReLU together, making only one single fused layer. So here in the fused layer, we execute ReLU function as soon as an output comes out from the convolution. So thereby, thereby saving a lot of memory bandwidth demand on this ReLU layer, because we don't really need to read the info feature maps on this ReLU layer. So this is what they call interlayer data reuse, and this kind of layer fusion technique is so common in the modern machine learning libraries or backend vendor libraries or graph optimizers. Then what's the problem here? Let's say we have a batch norm after convolution instead of a ReLU. If this is an inference case, BN can also be fused with convolution as like in a ReLU case. So this is because BN in inference is element-wise operation, because as variables used in the normalization, such as mean, variance, and gamma and beta, are all constants which are trained on the training phase. So as I mentioned, this is what contemporary ML libraries are doing already. However, in the training case, such fusion is not possible. The main reason is that the BN is no more element-wise operation in the training process, because we have to compute mean and variance per channel in this BN, and also in order to compute mean and variance, as they depend on every images in a mini batch, we need to sweep the entire mini batch for multiple times before normalization. So this kind of a data dependency within a batch requires off-chip memory accesses, making naive layer fusion less effective on training BN during, on BN during training. So then let's clarify the challenge of data dependency on this BN layer and our optimizations. So this is kind of a computational graph of a forward pass on a very common layer pattern in recent model. For example, here we have a conv VN activation and convolution layers. So here are feature maps, weights, and operator of a convolution. And the important here is that there are circles denoting memory readings and writings on entire input or the output feature maps of a batch. So after convolution, we get the mean first, reading input feature maps, and then we compute variance. So with that mean and variance, we can now get normalized alpha feature maps. And there are also following value or another convolution layer after that. So what is the challenge here? The challenge here is that strict data dependency between computing mean, variance, and the normalized alpha feature maps, each of which demands reading inputs multiple times, which become off-chip memory accesses, making BN hard to fuse with the convolution, the previous convolution layer. So this is our solution, what we call BN fusion and fusion BNFF. The idea is very, very simple. First, in fusion, we divide batch norm algorithm into two sub-layers, which is a sub-BN1 and sub-BN2. The sub-BN1 computes mean per channel and the variance per channel, while the sub-BN2 normalizes input feature map. And after that, the fusion comes, which is fusing each sub-BN layer with its preceding or the following layers. For example, here, sub-BN1 is fused with the convolution one, while the sub-BN2 is with the following layers, ReLU and convolution 2. So let me show you the optimizations implemented here one by one. The first of all is MVF, which is mean variance fusion. Actual formula is like this. It sweeps input feature maps 2 times to compute the mean per channel and the variance per channel. However, if we exploit this simple mathematical formula, which is computing second moment instead of a variance, we can now compute mean and the second moment together, reducing one memory read on a whole batch, as the dependency between the mean and the variance is gone. So in this MVF, since we calculate the sum of the squares, it becomes more susceptible to arithmetic errors at floating point, right? So in this case, we can use the double precision only for mean and the variance storage to avoid error. However, we observe that the floating point is good enough to train models with MVF. So further to the MVF, the sub-BN1 can be now fused with its preceding layer convolution one. So here we do this by accumulating each output of convolution to the stories for a mean and the second moment. And because the mean and the second moment is, they are per channel, their sizes are negligible compared to the sizes of the feature maps, we can save 2 option memory accesses total on the whole batch by fusing sub BN1 with the convolution one. So after MVF, another optimization is a ReLU convolution fusion, which is very similar to the convolution ReLU fusion, but actually this was done in a reversed order. So it's like in fusing convolution and ReLU case. This also removes input and output of the memory accesses on feature maps. So with that RCF, now we can fuse the ReLU and the convolution 2 with the sub BN2 layer, doing normalization and ReLU function and convolutional operation all together, thereby reducing 1 more memory accesses on the whole batch, totally 3 among the 6. So this is all about the forward pass. Then what about the backward pass? So backward pass is shown here, actually proceeding from the very right to the left. The main difference is that the memory accesses are not on the feature maps, but actually partial derivatives of feature maps, or gradients, what we call. So here in the backward pass, we can also apply the BNFF here, which is in a similar manner to the forward. However, for the full explanation, please refer to the paper for that because of the time constraints. So here, I just simply illustrate the reduced option memory accesses on the whole batch. So as fusion goes by, we save 1 read and write on partial derivatives from a sub BN1 and the convolution one, and 1 read more from the sub BN2, and also again 2 more from the ReLU and convolution 2. So although they are all different in their dimensions, roughly we can say 5 among those 9 read and writes. However, actually there are more memory accesses because we should count reading intermediate feature maps at the forward pass, and also there are memory accesses on computing derivatives of weight filters. So these are alpha. Then how did we evaluate our schemes on the modern CNNs? On those basic layer patterns in 2 CNN models, ResNet or DenseNet, we applied BNFF here. First, the 2 sub-BNs are shown in different colors. So first we apply RCF here, thereby fusing ReLU and the convolution layer together. Then after that, we apply BNFF. First, we apply fission by separating all BNs into 2 sub-BN layers, and then we fuse them to each neighbor, whatever it is, convolution or the L-twice layer. So this is the result. And here we see that finally one last remaining sub-BN1 in the composite layer, which can also be fused with concatenation by interconvergent fusion, what we call ICF. So this is the final figure on the 2 Shannon models. So this is our experimental setup. We evaluated on Skylake Xeon CPU servers having about 3 teraflops, and we also used Intercafe modifying MKLTNN, which is an open source DNN library and high performance, hand optimized in assembly level for Intel products. Also, we evaluated performance on the NVIDIA GPU. We did that by fusing multiple GPU kernels together in default gem implementations. For example, we can do per thread block reduction at the very end of the gem kernels on the convolution. So to implement that, we adopted and modified NVIDIA Cutlass, which is an open source gem library from the NVIDIA. So this is a chart of execution time on training with our schemes with ImageNet dataset. So y-axis is the execution time per iteration at batch 120, which is definitely the lower is the better. And the x-axis is incremental schemes in the forward and backward pass on those 2 target networks, DenseNet and ResNet. So here in the baseline in DenseNet, we see a great amount of time is spent in the BN and ReLU. And this RADO portion is gone, giving speed of around 9% with RCF RADO convolution fusion. We see that convolution portion, the yellow bar, increased a little. This is because the RADO function was merged into the convolution. So, however, the advantage from the fusion dominates, so we can get some speed up around it. On that number, mean variance fusion brings more speed ups in BN. And after that, the VNFF brings around 30% of speed ups in total, although the convolution portion increased a little, as the same reason as I mentioned. And also, this could be further pushed with the intercomposite fusion ICF, which is estimated. And what about the backward? In the backward, we can apply also the RCF fusion, radical convolution fusion, which brings a similar speed up to the forward case. And however, MVF is not available in the backward case because we don't compute mean and the variance in the backward case. There is no such fusion at the backward case. And after that, from the following two optimizations, we get less speedups compared to the forward pass in their numbers, because the main reason is that at the backward pass we should read multiple feature maps from the forward several times, so the memory access reduction ratio was kind of diluted. And also, this was a result from the DenseNet, and these are results from the ResNet. So the ResNet shows a similar tendency, but have less speedups compared to that of the DenseNet, because of the main reason is that the difference in the non-convolutional portions and the model differences. Also, in experiments in GPU, we have total speedups about by around 70% and 8% on those two models. Although we have the numbers, the speedups, our main focus is on resultant CPU. Why? Because the main reason is that the baseline performance of the gem implementation on the GPU is not even close to the closed source cuDNN NVIDIA library. So we think that the evaluation of our work on high performance custom CUDA kernels with the VNFF can be a future work. So to summarize, as non-conv layers are becoming more important on those deep and recent models, and the BN is especially the most heavy among them. We restructure it with our BNFF, BN fission and fusion, by dividing BN algorithm and fusing them into its neighbors, so that we complement existing layer fusion techniques, reducing memory bottleneck problem on BN in training. And so finally, we achieved speed of about 25% and 60% on each of DenseNet and ResNet on a CPU-based platform. So this is the end of my presentation. Thank you for listening.
Okay, go ahead.
Yeah, Min-Sik from IBM. So essentially, you made a trade-off between like a space complexity and then execution complexity.
Sorry, trade-off between what?
Space complexity and execution complexity. So essentially, you will increase the memory footprint here, right?
No. Actually, the memory footprint is not increased.
But don't you need to compute X and then X square and then keep them both at the same time?
Sorry? At what?
At the same time, you need to keep.
Yeah. The key,
right?
Yeah.
So essentially, at the moment, your memory footprint will be increased.
No.
So my question is, so by using this technology, I'm curious if I need to reduce my maximum batch size. And then if I need to reduce my maximum batch size, at the end of the day, it will hurt the throughput per device. So just I'm curious whether you have observed any change in the memory footprint.
That's an interesting question. So you're basically asking about the memory footprint on the MVF while we compute.
Yeah, for example, GPU has a 16 gigabyte, and then by somehow, if you increase your memory footprint, you have to reduce your maximum batch size from, let's say, from 100 to, let's say, the 60. So if that's the case, actual throughput per device may be decreased.
Actually, the mean and the variance, storage for the mean and the variance is quite large because it is per channel, so their size is negligible compared to the feature maps. So I don't think that that could be a problem in our MVF.
Go ahead.
Leon Colon from McKinsey. Have you considered how this method might impact internal covariate shift down the line by fusing these layers together? And if not, how do you think it might change?
Sorry, could you speak slowly?
Sorry. Have you considered how fusing batch normalization with the convolutional layer might impact internal covariate shift? And if not, I mean, how do you think it might change?
Actually, the covariance, we don't change the algorithm itself. We just give a little difference in the order they are computed. So I think that the covariance shift or something might be the same as before and after from our techniques.
Thanks.
Go ahead.
Hi, my name is Takeo Imai from National Institute of Informatics in Japan. Thank you for your interesting talk. My question is that is this technique effective also in inference phase? And did you try the speed up the in inference phase?
Inference.
Yeah.
As I said, in the inference case, as the batch normalization is the element-wise operation, which can be fused with the convolution or the other layers, which are already done in the modern ML libraries or graph optimizers. So our focus is on targeting the training. As
So maybe sometimes we want to fuse the networks and in training, both in training and inference. And so can I reuse the fuse the network in training and also in inference?
I mean that the fusion, this kind of a layer fusion, the existing layer fusion exists in the modern ML libraries or the graph optimizers, whatever it is, training or the inference. However, we extend it on the BN while training, so that's the key part of our talk. So I don't think that I think that inference already batch norm has no problem in that fusing with the other layers.
Thank you.
Yeah,
Okay, thank you.
Yeah.
Let's thank the speaker again.